Well, hello and welcome back to another episode of Quantitative Bytes. It's great to see you. I hope you're all doing well. Apologies for not having made videos for a little while. This is my first video in more than a month now, I think, which for me is kind of unusual. I do normally try to stick to a schedule of making one video a week, so obviously that slipped. I've just been busy with various things, you know, the day job and other things in life really just got in the way, and well, that's how it goes sometimes, I think. And yeah, and apologies for anyone out there that's been following my series, but we are now hopefully back, and I'm hoping to try and get back to something closer to the original schedule of posting once a week. I'm not sure if I'm exactly going to be able to achieve that right now, but we'll see how we go. Anyway, so in the meantime, I've not been completely inactive on Quantitative Bytes stuff, so I have done some work on the Spectrum Analyzer app that we were working on, if you remember from the previous videos. That's what we were looking at, and I haven't done as much really as I would have liked, but I have made some progress, so I thought I wanted to make a video today really just to talk about what I have done, and we can see how that's progressing. We've probably got maybe one, possibly two more episodes after this one to go before I think this project will be wrapped up sufficiently really to call it a day for this. You know, as I've said before, my objective really with these videos is to be inspirational more than anything. So I really hope to inspire at least some people out there to have a go at building things or making projects like this themselves, rather than it being necessarily a full-on tutorial. So I might not document everything that I go on to do, but I want to get it to a point where there is we have at least covered something that is fully functional, even if it's in only a very simple way. The one thing that I should note is that I have in the previous videos referred to this as a spectrogram, which is not strictly correct. Actually, of course, a spectrogram normally would be some form of time frequency representation. And whilst that is actually, strictly speaking, what we're doing, because our objective is to display frequency content over time, because we're doing it in an animated fashion rather than as a static two-dimensional image, it isn't strictly speaking a spectrogram. But I will try to remember that, and from now on we will refer to it as a Spectrum Analyzer app, which I think is what I called it originally in the first video. So one thing, the functionality that I've added since the last videos, I've added the command line capability, so that you can now, when you run the program, you can specify a file name of a .wav file, an audio file that you wish to open up, that you wish to read to analyze. And I've also added a specific class to manage the reading and handling, the reading of the WAV file and the handling of the data in that WAV file. Now, if you remember briefly, this is the class structure diagram that we have. And so this briefly summarizes the class structure diagram that we had before. So we have the CApp class we have here, and then this is exactly what we saw before. We have the specplot class, which then uses the rectangles from the QBLib2D from the other videos, and those inherit from objects. So I haven't filled those out completely because that's what we had before. The additional code that I've put in is highlighted here in red. So what I've done is added a QBWaveReader class to CApp, which you can see referenced there in red. Everything that's in blue is as it was before, and you can see there that's the outline of the QBWaveReader class. Now we're going to go over all of that when we come to look at the source code on the computer in a moment, so we're not going to go into it in any great detail, but I did mention at the first video of this series that I always like to do a class structure diagram just simply on my board like that, just to give me a feeling for how I think the project is going to develop. So when I decided to add an additional class to handle WAV files, it made sense that the first thing to do would be to modify the class structure diagram just to get a feel for how all of that's going to fit together. Right, well, I didn't really want to do a particularly long introduction, but just before we jump to the computer to have a look at the actual code, I just want to say that, as I always do, if you like this video, please do remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. I do try to post a video once a week, although that has obviously slipped recently, as I've already said, and perhaps is not going to be quite so regular over the next few weeks, but we'll see. We'll see how we go. Anyway, without much further ado, let's jump over to the computer and let's have a look at the code. Okay, so here we are at the computer, and the first file that I wanted to look at is actually main.cpp. Now this is one that we don't normally really talk about very much because it hasn't had to change until now. The reason that we've changed it, or the reason that I've made changes to it now, is because we want to be able to accept command line arguments. So just to show you what I mean, I want to be able to run my program in such a way such as like this. So I call ./main, that's just the name of the executable, and then I want to be able to specify the name of the WAV file that I want to open. And in order to do that, we have to modify main.cpp so that we can accept and process command line arguments. And the standard way to do that in C++ is simply with this notation in the declaration of the main function. And then we simply test if that the argc, which means the argument count, the number of arguments, if it's exactly equal to 2, then we know that we want to pass argument value number 1 to the execute function of the app. So if you remember previously, all we did was we just ran the app.execute, and then that initiated the process and everything else. So execute, of course, comes from the capp class that we talked about previously. And what we do now is we pass to that argument number the value of argument 1, which is going to represent our file name. If we don't have exactly 2 arguments passed, then we display an error message to say that the correct usage should be main and then filename.wav. And that's that. So that's everything that we need to do in main.cpp. Made some changes to capp, so we want to talk about those very briefly. So in capp.h, the first thing that I've done is modified the execute method here so that now it accepts char* file name as input, which is, as we see from main.cpp, when we call the execute method, we pass to it the argument as we've just seen. I've also added a vector of complex doubles called msignal. If you're confused about that data type, that is, go back and look at the previous video I've done. I'll put a link in the description below on the discrete Fourier transform, how the discrete Fourier transform works with code in C++. And so we're just following the standards that I've already adopted from that. And we then have just one final thing, an instance of our QBWaveReader class that we're going to talk about in a moment called mWaveReader or mWaveReader. And that is actually all of the changes to capp.h. It isn't very much. Now, before we talk about capp.cpp, I think this would be a very good point at which to actually talk about the QBWaveReader class itself. So we've already seen in the introduction the class structure diagram. So this is the QBWaveReader.h. Now QBWaveReader exists in the QBSpecLib folder or directory of the project, which is, we're already in that, so we see it here. So the files that we had before were specplot.cpp and specplot.h, qbdsp.cpp, qbdsp.h, and qbspeclib.h, which is the master header file for everything. And we've added now QBWaveReader.cpp and QBWaveReader.h, and that, as I say, exists within the QBSpecLib subfolder for this project. So in QBWaveReader.h, we have really just the very basic things. They include guards, as we have in every include file. We just include then a bunch of stuff. We need SDL, vector, and complex from the standard libraries. And then we're putting this in the QBSpecLib namespace. We declare our class QBWaveReader, and we have our public functions here. We have, of course, a constructor and a destructor. And then, as we saw in the class structure diagram, we have our functions to open a WAV file, which accepts as input a char* file name, returns a Boolean. Now that's useful because it means that if for some reason we're unable to open the file that the user has specified, we simply return a value of false. So whatever the calling function, whatever the calling code was, we can know that the open file failed. We then have functions to set chunk size and set chunk overlap. We're going to talk about those in a moment when we come to look at QBWaveReader.cpp. And we have get next chunk, and this is simply the function that's actually going to return a chunk. And actually, well, I'll mention that the reason we're doing it this way is we want to be able to pass to our QB specplot, our instance of the specplot class, we want to pass to it chunks of the data at a time rather than obviously the whole thing. So the QBWaveReader class will read in the WAV file, and then it provides this very simple functionality to return sequential segments or chunks of that data, which are obviously smaller than the whole set. And so we set chunk size, so that's how many samples we want in each chunk, and chunk overlap is obviously how much overlap we want between them. And then the functionality, the idea is that you simply call get next chunk every time you want to get the next chunk, and it takes care of incrementing that through the raw data and returning a signal pointer to us, or yes, returning data in the form of a vector of complex doubles, which is the format that we used, if you remember from the previous videos, for the specplot class. And then, of course, we just have our private member variables. We need to store the details for SDL audio spec and SDL audio format. These are well described, actually, in the documentation for SDL2 that talks about how to read data from WAV files. So I don't intend to really talk about those very much. I will put a link in the description below to the relevant pages in the SDL2 documentation, and I really recommend you go and check that out. And then we just have our private variables. We store the file name, we obviously store the chunk size, overlap, the current chunk index, because we're going to be incrementing through them every time the user calls get next chunk, so we need to keep an index of where we are. And previous end is simply the end of the last chunk that we returned, and have data is simply a boolean that we're going to use to store whether we actually have valid data loaded or not. Okay, so let's jump into the CPP file. Now this is all pretty standard stuff, there's not too much to talk about here. In the constructor, we simply initialize our default parameters, so the current chunk index begins at 0. We're, for the moment, hard coding a chunk size of 256 samples with an overlap of 128. The previous end obviously begins at 0, and have data initially starts at false, which makes sense. In the destructor, here we simply test that if we actually have data, and this is why we need the mHaveData flag. If we have data, then we use the SDL_freeWav function to free the buffer, which is stored in mDataBuffer. And open file, this function is simply responsible for actually loading the WAV file. So the first thing we do is we store the file name. You'll note actually that we only have a default constructor, so there are no parameters passed when we construct an instance of this class, and we then use the open file method to specify what file we want to open, and that will then go about opening the file when we do that. So the first thing we do is we store the file name, and then we use the SDL_load_WAV function to open that file, and we pass to it pointers to the data type, data buffer, and data length variables that we created here. If we go back to QBWaveReader.h, so we have mDataType, mDataFormat, and mDataLength defined here, and so we simply pass pointers to those into the SDL_load_WAV function, and that will populate those with the necessary data. Data buffer will contain the data, data type contains all the information that we need to know about the structure of the WAV file. WAV files can be quite complex, and data length is obviously going to be the number of bytes that we've read. If we do that and we get null PTR back, then we know that something has gone wrong, so we simply return false. Otherwise, we modify haveData to true to show that we have opened the data successfully, and we extract the data format into the data format variable from mDataType.format, and we return true to indicate that everything was successful. Okay, so pretty straightforward really. Like I say, the SDL2 documentation for load_WAV tells you a great deal of information about these things, and you feel, just browse around the docs. It's all described there. I'm not going to repeat anything that they've said, obviously, so yeah, like I say, I'll put a link in the description below to that. And the functions then we have for set chunk size and set chunk overlap, they're really basic. They simply accept, both of them accept as input just an integer, and then simply store that in the relevant internal variable. So that's that. The real work is done here in the QBWaveReader : get next chunk function. Now this accepts as input a pointer to a vector of complex doubles, and this is the where we're going to actually output the chunk of data, the next chunk of data. And this is the format, as I've said before, the format that we used for QBSpectPlot, for the specplot class, that simply accepts an input of this type and will compute the necessary Fourier transform of that and create the display of it automatically. Okay, you'll see how that works. When we come back to look at capp.cpp, we'll see why I've structured it this way. I think it's a fairly logical way of doing it, but it's maybe not the most optimum. Anyway, the first thing we do is check that we actually have some data to return. So we check that the data buffer is, if it's equal to null PTR, then we don't have anything, we simply return false. So that just adds a little bit of safety. The first thing then we're going to do, assuming that we have some data, is we need to clear any previous data that's been put into signal. So we use signal, we use the clear method from signal, which signal is an instance of the vector class in the standard library, so that's easy, and that will just clear everything. We then compute our start index, so this is the index of the sample index in the wave file that we're going to start with, and we take that as either being the maximum of the previous end minus the overlap. So prev end, this is the end of the last chunk that was extracted from the data, and we obviously subtract from that the overlap because we're allowing for some overlap between each of these chunks as we go. But that, if mprev end is obviously equal to 0, if we're at the beginning of the file, then this is going to result in a negative number. We don't want that. So we simply take the maximum of this value or 0, and simply start index will then either be either this value or 0, depending on which was the largest. So that's straightforward. And we then compute the endpoint of the next chunk, which is simply going to be the start index that we've just computed plus the chunk size. So that's very straightforward. And then now we modify mprev end to be equal to that end index, so that we can then next time this function is called, we will use the previous value there for prev end when we come to compute the start index. Okay, and I've just put in a comment here which just explains that, of course, these indices are in terms of samples and not bytes. So the SDL load WAV, when we read in the WAV file, it reads it in as raw bytes, not actual samples. Samples could be 16-bit, we could have multiple channels, all of that sort of thing. So the raw bytes that we read in are not necessarily going to be equivalent to the actual samples. So it means when we come to actually extract the samples from the buffer, we have to take into account how many bits there are per sample, as well as how many channels there are in the WAV file. And for now we're assuming either single channel, or we simply ignore everything except the first channel. So if you pass, at the moment, if we were to pass to this a stereo wave file, it's only going to produce a spectrum analysis from the one channel, and it will ignore the second channel, which will come, and I'll probably look at ways of dealing with that later. Okay, so what we actually need to do now is to extract the samples from the buffer and convert them to the appropriate format of complex doubles. So first of all, we need to know how many bytes we have per sample, and we can get that using the SDL audio bit size function and passing to it the mdata format variable, and then we simply divide that by 8 and static cast that to int. So that's going to give us the number of bytes that we have per sample for our wave file, and we need to know the number of channels, so we get that from the data type variable. And then we're going to compute the step size that we will use to loop through the buffer. So this is simply going to be the number of channels multiplied by the bytes per sample. So if we know that each sample consists of 2 bytes, then obviously when we're looping through the raw bytes, we want to loop through with a step of 2. If we have 2 bytes per sample and 2 channels, then we know we need to loop through with a step size of 4, so that we're extracting only the bytes that we want for the particular channel that we're interested in. I think if you work that out on a paper, if it's confusing, I think that will be quite clear. And then we compute the byte start index and the byte end index, remembering that start index and end index that we computed here are in terms of samples. We simply multiply those by byte step, and that will give us the equivalent in raw bytes. And then what we're simply going to do is loop through our buffer and extract the samples that we need. So we start with current index is equal to byte start index, and we define a short int for our current sample, and we're using a while loop. So we'll loop while current index is less than byte end index, so while it's less than what we've computed as the index of the byte that we're going to stop on. And of course also check that current index is less than mdata length minus 1. Okay, to make sure we don't try to read beyond the end of the buffer, which would obviously generate a segmentation fault. And we're then going to extract the current sample, and note that for now we're assuming either just 8 or 16-bit data. If we were going to deal with wave files that for some reason may have greater than 16-bit data, then obviously we would need to use a loop to extract the bytes and convert it. Be a little bit more complicated. So the first thing we do is simply see if bytes per sample is greater than 1, so we're assuming it's going to be 2. Then we need to convert the individual bytes into a 16-bit number, and of course the way we do that depends on whether the data are encoded as big endian or little endian. So we can tell that using SDL audio is big endian function and passing it the mdata format variable. And if that's true, then we know we have big endian, so we convert the data this way. So take the byte at current index and use the bit shift operator to shift that by 8 bits, and then we add to that byte the byte at current index plus 1. If we have little endian encoding, we do exactly the same thing, just the other way round. Okay, so that's pretty straightforward. If we have the case that we only have 1 byte per sample, then we simply extract the byte at the current index, and that's everything that we need to do. So by the end of this block of code here, where are I? So by the time we get to the end of this block of code, what we have now is that current sample will contain the current sample, whether it's from 16-bit or from 8-bit, it will now contain all of the data that we need. So what we need to do now is simply to convert that into the complex double format that we're going to use for our signal. So we do create a variable called signal sample of type complex double, and then we static cast a double current sample and pass it. Obviously the imaginary part is 0, and we're just passing that into the real part there, okay? And then we push that back into signal, remembering that signal is an instance of the vector class in the standard library, so we just push back our current sample, and then we increment byte current index by the byte step, and then we simply repeat our loop until we reach the end of our while loop. And actually that's everything. And if everything works successfully, so if current index is greater than or equal to m data length, then we return false, because there's no more data to read. So we want the whatever the calling function is to stop trying to call this function, get next chunk. Okay, so the idea is that the calling code will sequentially call get next chunk every time it wants to process a frame of the data or a chunk of the data. It calls get next chunk, and this will return the next chunk until it's no longer possible. Once we reach the end of the data, it returns false, which will indicate to the calling code that we can't extract any more data. Otherwise we return true, and then the calling code will know that we can just carry on. Okay, so that's really everything from the QBWaveReader class. And if we look in just in capp.cpp, we can get a feel for how that's implemented. All I've done is everything here is exactly as it was before, except perhaps I'm now using 128 bins. The previous example, I think I had 64 for the spect plot, but we've talked about that before. What has changed here is the execute function, which now accepts as input char* file name. All we do is we store the file name, and then everything else there is the same. What we do is we then we use the WaveReader class to attempt to open the file. So we call mwavreader.openFile and we pass to it the file name. If the result of that is false, then we know we had an error, so we simply display an error and return -1 so that we stop the execution. Otherwise we carry on, and we simply then call the getNextChunk function from the WaveReader class and pass to it a pointer to the signal. Remember, if we look in capp.cpp, signal was defined here, okay? So that's very, very straightforward. And then everything there is exactly as it was in the previous video. The only point where there's some more differences in the tick method, so this is called every time through our main loop, and this simply clears the window and calls mspecplot to set data. And you see, this is the functionality that we went before. So we have our specplot class that's responsible for creating, actually calculating the discrete Fourier transform and creating the display. And every time we want to do that, so every time we come through tick for every frame in our animation, we call the setData function from mspecplot and we pass to it msignal. So I think hopefully you can see how this is going to work. And then once we've done that, we call the render method on mspecplot to actually generate the display, and SDL render present, just make sure that we update it. Once we've done all of that, we want to extract the next chunk of data. So what we're going to use is the getNextChunk function from the mwavreader class, or instance of the QBWaveReader class, and we pass to it a pointer to msignal. So if this is successful, that will populate msignal with the next chunk of data, and then the next time we come through tick, that is going to be passed to specplot, which will then be rendered, and that will produce the next frame of the animation. If, on the other hand, that is unsuccessful, if we get false back, as we just saw in QBWaveReader, if we go right down to the end, we return false here if we reach the end of the file. So if this returns false here, then we set m is running to false, which will mean that we will stop the execution. We display a message to say end of file reached. Otherwise, we don't really need to do anything. And actually, that's it. That produces all of the basic functionality that we need. And if we go ahead and compile that code and run it, in fact, I've already compiled the code, so we don't need to worry about that. So this is in the main file, and we have our main file as has already been done. Let's just double check. Let's just run make clean to tidy everything up. And let's run make to compile everything. Now, one thing that I just want to mention while that compiles is that I'm going to show this now using a very basic test signal that I generated in Python. There's quite good documentation online for how to create and write WAV files from Python using using the SciPy libraries. So I'm not really going to talk about that. I just used some very basic code to create a standard linear chirp, and I wrote that out as a .wav file, and that's the code that we're going to analyze here. So that's compiled everything. If we look, so I have test signal.wav, this is the wave file that I want to read, and if I run my code /main test signal.wav, if we run that, I'm going to have to move that over, bring that over so you can see it. What we get now is this animated display. I don't know if you can see all of that. So that is looping over all of the samples in our signal, and as it's a linear chirp that goes from 5 kilohertz up to 11 kilohertz, we get this animated display as it goes, and then it will end, and it displays the message end of file reached. Okay, so that's pretty much exactly the functionality that we want. A couple of things, if we were to pass to it a file that isn't a valid WAV file, so let's just pass to it main.cpp, I mean that's really silly. That should display, yep, appropriate error message, failed to open .wav file, so we see that that works. The other thing to mention is that obviously this runs very slowly, so the test signal that I created is only 1 second long, and it obviously took a lot more than 1 second to actually generate all of those frames of our animation, and that is really something that would need to be improved. I mean, for what I'm trying to do, I'm not really that bothered about real time, so it doesn't really matter for me. But if you wanted this to run in real time, I mean, the first thing really to look at would be to swap the DFT code for a fast Fourier transform. I haven't done that, as I say, because I'm not that concerned about, about real time. All I really want is code that I can run in this way, using a command like this, and I want it to generate all of these images, and then ultimately I want to write those images out so that I can then overlay them onto a video to make, for example, the kind of spectrum analyzer display you often see overlaid onto music videos on YouTube and whatever. That's really what we're aiming for. Now, I personally don't mind if it takes a few minutes, or even a few tens of minutes. It's not going to be a problem for me to actually do that, so that I'm not really going to worry about trying to make this code run in real time. But as I say, for what I want, this is perfectly functional. Okay. So there we go. That's really everything that I wanted to talk about today. I haven't got as much done, perhaps, as I would have liked to have done since the last video. But yeah, we've implemented the WaveReader class, so we can now open and read data from a WAV file, and we can actually display the spectrum analysis of that as we go. So you start to see how the Spectrum Analyzer app is really starting to take shape. Obviously, the performance isn't really everything that I would want it to be. It would be better if it was capable of running in real time. It clearly isn't. And part of that, of course, is because we're using just the discrete Fourier transform. We could switch that out and use a fast Fourier transform. That would give us a big performance improvement. And we could also optimize other parts of the code. The thing is, really, for me, real time has never been my objective with this. It's always, my intention has always been to simply a simple app that I can run from the command line, pass it a WAV file, it will generate a series of images that I can then overlay onto a video or something like that, as you see the sort of classic Spectrum Analyzer kind of display on music videos on YouTube. That's the sort of thing I was aiming for, and I don't really have any need for that to run in real time. So for what I want, this code is perfectly satisfactory. Really just leaves me to say thank you very much for watching, and I really hope you've enjoyed this video. It's been a great pleasure making it, and I really look forward to seeing you in the next episode. I think we've got at least 1 or possibly 2 episodes to go for the Spectrum Analyzer, and then I'm probably going to move on to something else, but we'll see how we go. Anyway, so thank you very much for watching, and I'll see you in the next video. Bye!